Armor-piercing fin-stabilized discarding sabot, APSTS, is a type of kinetic energy penetrator ammunition used to attack modern vehicle armor. As an armament for main battle tanks, it succeeds armor-piercing discarding sabot, APDS, ammunition, which is still used in small or medium-caliber weapons systems. Improvements in powerful automotive propulsion and suspension systems following World War II allowed modern main battle tanks to incorporate progressively thicker and heavier armor protection systems, while maintaining considerable maneuverability and speed on the battlefield. As a result, achieving deep armor penetration with gun-fired ammunition required even longer anti-armor projectiles fired at even higher muzzle velocity than could be achieved with stubbier APDS projectiles. History. Armor-piercing discarding sabot, APDS, was initially the main design of the kinetic energy, K, penetrator. The logical progression was to make the shot longer and thinner to concentrate the kinetic energy in a smaller area. However, a long, thin rod is aerodynamically unstable, it tends to tumble in flight and is less accurate. Traditionally, rounds were given stability in flight from the rifling of the gun barrel, which imparts a spin to the round. Up to a certain limit, this is effective, but once the projectile's length is more than 6 or 7 times its diameter, rifling becomes less effective. Adding fins like the fletching of an arrow to the base gives the round stability. The spin from standard rifling decreases the performance of these rounds. Rifling diverts some of the linear kinetic energy to rotational kinetic energy, thus decreasing the round's velocity and impact energy, and very high rotation on a fin-stabilized projectile can dramatically increase aerodynamic drag, further reducing impact velocity. For these reasons, APSTS projectiles are generally fired from smoothbore guns, a practice that has been taken up for tank guns by China, India, Israel, Italy, Japan, France, Germany, Turkey, Russia, and the United States. Nevertheless, in the early development of APSTS ammunition, existing rifled barrel cannons were used, and are still in use, such as the M68-105mm cannon mounted on the M60A3 main battle tank. To reduce the spin rate when using a rifled barrel, a slip obturation ring, is incorporated that allows the high-pressure propellant gases to seal, yet not transfer the total spin rate of the rifling into the projectile. The projectile still exits the barrel with some residual spinning, but at an acceptably low rate. In addition, some spin rate is beneficial to a fin-stabilized projectile, averaging out aerodynamic imbalances and improving accuracy. Even smoothbore-fired APSTS projectiles incorporate fins that are slightly canted to provide some spin rate during flight, and very low-twist rifled barrels have also been developed for the express purpose of firing APSTS ammunition. Another reason for the use of smoothbore and very low twist rate guns is that the most effective precision-shaped charge designs, heat munitions, lose armor-penetrating performance when rotating too fast. These deep penetrating shaped charges also require fin stabilization, although less precise and less effective spin-compensated shaped charges can be designed to function properly in a spin-stabilized projectile. Design. K penetrators for modern tanks are commonly 2 to 3 cm in diameter, and can approach 80 cm long. As more structurally efficient penetrator sabot designs are developed, their length tends to increase, in order to defeat even greater line-of-sight armor depth. The concept of armor defeat using a long rod penetrator is a practical application of the phenomenon of hydrodynamic penetration, see hydrodynamics. In a literal sense, it is fluid penetration, based simply on the density of the target fluid and the density and length of the penetrator. The penetrator will continue to displace the target to a depth of the penetrator length times the square root of the penetrator to target densities. One observes immediately that longer, denser penetrators will penetrate to deeper depths, and this forms the basis for the development of long-rod anti-armor projectiles. Despite practical penetrator and target materials not being fluids, at sufficiently high impact velocity even crystalline materials begin to behave in a highly plastic fluid-like manner, so many aspects of hydrodynamic penetration do apply. Anderson 1998, Anderson 2016. The important parameters for an effective long rod penetrator, therefore, are very high density with respect to the target, high hardness to penetrate hard target surfaces, very high toughness, ductility, so the rod does not shatter on impact, and very high strength to survive gun launch accelerations, as well as the variabilities of target impact, such as hitting at an oblique angle and surviving countermeasures such as explosive reactive armor. The development of heavy forms of reactive armor, such as the Soviet, later Russian, Contact 5, which are designed to shear and deflect long rod penetrators, has prompted the development of more complex kinetic energy penetrator designs, particularly in the newest U.S. anti-tank rounds. Nevertheless, although penetrator geometry may adapt to reactive armor countermeasures, the materials of choice for deep penetrating long rod kinetic energy projectiles remains tungsten heavy alloy, WA, and depleted uranium alloy, DU. Both materials are very dense, hard, tough and ductile, and very strong, all exceptional qualities suitable to deep armor penetration. Nevertheless, each material exhibits its own unique penetration qualities that may or may not be the best choice for any one anti-armor application. For example, depleted uranium alloy is pyrophoric, the heated fragments of the penetrator ignite after impact on contact with air, setting fire to fuel and or ammunition in the target vehicle, contributing significantly to behind armor lethality. Additionally, DU penetrators exhibit significant adiabatic shear band formation. A common misconception is that, during impact, fractures along these bands cause the tip of the penetrator to continuously shed material, maintaining the tip's conical shape, whereas other materials such as unjacketed tungsten tend to deform into a less effective rounded profile, an effect called mushrooming. Actually, the formation of adiabatic shear bands means that the sides of the mushroom tend to break away earlier, leading to a smaller head on impact, though it will still be significantly mushroomed. Tests have shown that the hole bored by a DU projectile is of a narrower diameter than for a similar tungsten projectile, and although both materials have nearly the same density, hardness, toughness, and strength, due to these differences in their deformation process, depleted uranium tends to outpenetrate an equivalent length of tungsten alloy against steel targets. Nevertheless, the use of depleted uranium, in spite of some superior performance characteristics, is not without political and humanitarian controversy, but remains the material of choice for some countries due to cost considerations and strategic availability compared to tungsten. Complicating matters, when foreign deployment of military forces or export sales markets are considered, a sabot designed specifically to launch a DU penetrator cannot simply be used to launch a substitute WA penetrator, even of exactly the same manufactured geometry. The two materials behave significantly different under high pressure, high launch acceleration forces, such that entirely different sabot material geometries, thicker or thinner in some places, if even possible, are required to maintain inbore structural integrity. Typical velocities of APFS rounds vary between manufacturers and muzzle length/types. As a typical example, the American General Dynamics QA1 has a muzzle velocity of 1740 m/s, 5,700 feet/s. This compares to 914 m/s, 3,000 feet/s, for a typical rifle, small arms, round. APFS rounds generally operate in the range of 1,400 to 1,900 m/s. However, above a certain minimum impact velocity necessary to overcome target material strength parameters significantly, penetrator length is more important than impact velocity, as exemplified by the fact that the base model M829 flies nearly 200 meters/sec faster than the newer model M829A3, but is only about one-half the length, wholly inadequate for defeating state-of-the-art armor arrays. Often, however, the greater engineering challenge is designing an efficient sabot to successfully launch extremely long penetrators, now approaching 800 mm in length. The sabot, necessary to fill the bore of the cannon when firing a long, slender flight projectile, is parasitic weight that subtracts from the potential muzzle velocity of the entire projectile. Maintaining the inbore structural integrity of such a long flight projectile under accelerations of tens of thousands of Gs is not a trivial undertaking, and has brought the design of sabots from employing in the early 1980s readily available low-cost, high-strength aerospace-grade aluminums, such as 6061 and 6066 T6, to high-strength and more expensive 7075 T6 aluminum, Marujing steel, and experimental ultra-high-strength 7090 T6 aluminum, to the current state-of-the-art and incredibly expensive graphite fiber reinforced plastics, in order to further reduce the parasitic sabot mass, that can be nearly half the launch mass of the entire projectile. The discarding sabot petals also travel at such a high muzzle velocity that, on separation, they may continue for many hundreds of meters at speeds that can be lethal to troops and damaging to light vehicles. For this reason, even in combat, tank gunners have to be aware of troop overfire safety. The counterpart of APFS in rifle ammunition is the sabot flechette. A rifle firing flechettes, the special-purpose individual weapon, was under development for the U.S. Army, but the project was abandoned.
Please subscribe and thanks for watching.